question 22 introduces this equilibrium, and it tells us that as the temperature increases, we get more 2-methylbutene, so more of this one. So what that means is that it shifts in the forward direction, or to the right. You can say it either way, shifts in the forward direction or shifts to the right as the temperature increases. Okay, it's important to write that down. I mean, it seems like you're almost just restating the question, but showing that you know that you have to shift it into that kind of language of shifting equilibria is important. And then you apply Le Chatelier's principle, which says that when you increase the temperature, it will try to oppose that, and the way it opposes it is by going in the endothermic direction, because endothermic takes away heat and therefore opposes the temperature increase. So that's your second bit of information, that it shifts in the endothermic direction to oppose a temperature increase. And really all you're being asked to do is to put those two bits of information together and say, right, well, we know it goes in the forward direction, we know it goes in the endothermic direction, therefore fairly obviously that implies that the forwards is endothermic. And remember that delta H for an endothermic reaction is positive, so if it's positive in the forward direction, that's the value that we give for the reaction. So we say that delta H is positive, is what we can conclude from that bit of information. Okay, now it wants an enthalpy profile diagram for this reaction, including the effect of a catalyst. So an enthalpy profile diagram is a sort of a graph where you have enthalpy on this axis. The axis along the bottom doesn't really mean very much at this level, but if you want to label it something, you can call it progress of reaction or reaction coordinate or something. It's not time, because reactions don't occur sort of linearly in time, so I think that's confusing. To don't put time, but you can put, if you like, progress of reaction along the bottom. And then you've got to put on your states just labelled as levels on the enthalpy profile diagram, and they need to be labelled quite precisely, so don't just write the word reactant or something. That's got to have the substance there, and in this case it's that alcohol. And then we've just worked out in the previous part that delta H is positive. So delta H is the enthalpy change between there where we start and where we end up. So if it's positive, it means that the product is up there. Okay, so this is our product, which is the alkene plus water, steam. And it didn't actually ask us to label delta H in this particular question, but normally you would be asked to do that. So just to make that clear, that's delta H then. So draw an arrow spanning the full gap from where you start to where you finish and label it clearly. So that would be delta H, but as I say, you didn't actually need that in this particular case. What you did have to do was mark on the activation energy. So the idea here is that there is some kind of pathway which leads from the reactant to the product. And that will always involve going through a state that has higher energy than either of these. And so what you need to do is to draw on there a pathway, something like that. Okay, and that takes you through the idea that you have to put in a lot of energy and then you get, in this case, some of it back. And the activation energy is the height of that hill. It's how much energy you have to put in from where you started to reach the top of the hill. Now, the problem is that it tends to get very crowded and messy in there. So the cleanest way to do this is just to extend this across with a dotted line and then mark the top of the hill. And again extend that across with a dotted line. And then over at the side where you've got plenty of room, you can draw in an arrow spanning that whole range. And that is the activation energy, which we write as E subscript A for short. So that's the activation energy for the reaction, normally when you haven't got the catalyst there. What the catalyst does is introduce a new reaction pathway that has a lower activation energy. So in other words, there's going to be a new pathway still leading from here to there, so delta H hasn't changed, but now going over a lower hill. And that's what a catalyst does. So again, we've still got this level here at the bottom, but now the height of the hill is just this much. So again, if you draw the dotted line across there, we can label this as the activation energy with the catalyst, which is lower. Now the question asked you to sort of use the diagram to explain how the catalyst influences the rate, and it doesn't quite do that so far. It uses the diagram to tell you that you have a lower activation energy when the catalyst is there, but that doesn't explicitly say how it influences the rate. So you need a bit of writing as well. And specifically what you need to say is that the catalyst introduces a new pathway with a lower activation energy, which is what the diagram shows you, but then you explain that that means that the frequency of successful collisions will therefore increase, and therefore the reaction will go faster. So it's that link to a lower activation energy means there's a higher probability or a higher frequency of successful collisions, and therefore the reaction will go faster. Part C, we have to explain why 2-methylbutantuol, which is this, can dissolve in water, whereas 2-methylbutuene, which is this, can't. So this is about hydrogen bonds. Remember that things will only dissolve in water if they can form interactions with the water which are similar in strength to the hydrogen bonds between the water molecules themselves. Otherwise the water would rather just stay hydrogen bonded to itself and will reject the thing that tries to dissolve. So this one can't, that's the problem, because all it could form would be induced dipole-dipole forces, and the water just doesn't want to know. But this one, because it has an OH group, can form hydrogen bonds. So that's the key thing. First of all, you state that 2-methylbutantuol can form hydrogen bonds to water molecules. Don't just say can form hydrogen bonds, because the examiner will say, why should I care? So you've got to specify that it's able to form hydrogen bonds to water molecules, which enable it to dissolve, whereas this can't. And again, say that explicitly. So this can form hydrogen bonds to water, whereas this can't, and that's why this can dissolve. Now the diagram for hydrogen bonding, the important thing, remember, is that you have to show the OH group explicitly, and that's going to form a hydrogen bond, which you represent by a dotted line to your water molecule, which is going to be like that. And the key things you have to put on there are the dipoles. So you're going to have delta minus, delta plus for this OH, delta minus and delta plus for these OHs as well. So all those partial charges need to be on there, and also you need to show it pointing at one of the lone pairs on the oxygen. Okay, so you have your hydrogen bonds pointing specifically at one of the lone pairs, and so that's the diagram that you need for illustrating the solubility. The next thing it asks us for, this is part D, is for an equation for the polymerization of that alkene. So all you really have to remember then is that when an alkene polymerizes, the pi bond breaks, so we lose the pi bond from there, and instead you form two new sigma bonds, one from each end of where the pi bond was. So you'll have one like that and one like that, and they will link through to the next repeat unit in the chain. So that's what the repeat unit is. Make sure your linker bonds stick all the way through the brackets like that, and that's going to be repeated n times, where n represents a large number. We're not defining exactly how many. To turn that into an equation, we need to then put the monomer back on this side, which was this. So we have n moles of that, turns into 1 mole of this containing n repeat units. If you don't like doing that with skeletal formulae, it does look, I guess, slightly weird drawn out like that. You can just turn this into a more conventional picture. So remember, you put the alkene group at the heart of it, and you think, right, at this end I've got a CH3 and a hydrogen. At this end I've got two CH3s. And you can say, right, I'll have n lots of that. And then again, it's very simple, because you just go through the same line of thought and say, right, where I used to have the alkene group, I now just have two linker bonds sticking out like that. The other four things are just the same as they were before. So I've got CH3, CH3, H, and CH3. And again, you put the brackets so the linker bond sticks right through it, and n lots of that. So if you're more comfortable writing out polymers like that, that's absolutely fine. Part E wants us to first of all write down the structure of the two possible products when HCl adds to that alkene. So the issue here, of course, is that when you add HCl to that, it could add this way across the double bond, so hydrogen onto that end and Cl onto that end, or it could add the other way around, Cl onto this end and hydrogen onto that end. So your two possible products will either be the same carbon skeleton but now no double bond, and instead, if it adds the top way, you'll get the Cl onto there, hydrogen on the other end, but obviously you don't see that in the skeletal formula. And if it adds the bottom way around, the chlorine will add onto that one, same one as the extra methyl group, so we're going to get that. So those are the two possible products. And then it asks us to propose the mechanism for the formation of one of them, so it doesn't matter which one you choose. So let's just use the bottom one. So you draw out your alkene, and you remember that this is electrophilic addition, which means that the electrophile, which is HCl, accepts a pair of electrons, and so the end of it that's going to do the accepting is the delta positive end. Okay, because it's the delta positive hydrogen that's going to be attractive to this pair of electrons. So you've got to get that the right way around. If you just think about what's happening, that you're having to attract a pair of electrons out of the double bond, then it becomes obvious it must be attacking that way round. And then you draw a curly arrow very carefully, showing that you get a pair of electrons coming from the double bond to the hydrogen. Okay, so you've got to draw the curly arrow very accurately. At the same time as that, because the hydrogen can't form two bonds, if it's going to accept that incoming pair of electrons, it has to let go of this pair that it's sharing with the chlorine. So you get a second curly arrow that goes like that. And again, it's got to be accurate. It's got to come from the bond, showing that it's that bonded pair which is now moving out onto the chlorine. Sorry, I realised I got the charge wrong on the chlorine there, so that wants to be delta minus. So that's the detail of what you need in the first step of the reaction. And that gives you at this point just an intermediate. It doesn't give you the full product yet. So at this point the hydrogen could have added on to either end, and whichever end the hydrogen doesn't add on to will at this point be positively charged. So if we put the hydrogen adding on here, that means we're going to get the positive charge on that carbon there. The chlorine, meanwhile, has become a chloride ion, because what used to be the bond has now become that lone pair, so you show the lone pair on there. And you can see that to complete the reaction is now very simple, because this carbon is short of a pair of electrons, this one's got an extra pair of electrons, and so it can simply plug that lone pair of electrons in there to complete the reaction, and that will give you this product. So there is your mechanism complete. So it's about accuracy with the curly arrows really is the key to that one. Part 3 then wants us to explain which of these two alternative products, which you identified earlier on, will be the major one, and explain that in relation to this mechanism. Well, you can see that this product was formed via this intermediate, which is called a carbocation, because it's got a positive charge on the carbon. And specifically, this is a tertiary carbocation, because the carbon with the positive charge is bonded to 3 other carbons. So you just explain that this is formed via a tertiary carbocation. So the language is important here. It's not that the product is tertiary that matters, it's the carbocation that it's formed via which is going to determine which is the major product. So you say formed via a tertiary carbocation. This one, on the other hand, you can see that the intermediate that resulted from would be this, because the hydrogen would have added onto that end, so you'd have the positive charge here where the chlorine ends up, and that's just a secondary carbocation, okay, because the carbon with the positive charge has just 2 other carbons attached. So you say this is formed via a secondary carbocation. And comparing those two, you just remember that what happens is that each time you add an extra carbon on around the periphery of that positive charge, it helps with the stability of it. So the tertiary carbocation is more stable than the secondary one, which means that it will be more easily formed and therefore will lead to the major product. And that's the idea. Okay, so this one is the major product. Okay, so that's a very typical kind of question, so you've got to make sure that you've practiced that, and it's getting the language that deciding which one is the major product depends on the stability of the intermediate. That needs to be very clear. So you say which type of carbocation each of the possible products would be formed through. There's no point just focusing on this one because it's the comparison that matters. Tertiary is more stable than secondary, therefore the tertiary one is more easily formed, therefore it leads to the major product, which is that one.